Consider the line L1 defined by the Cartesian equation, shows that the point -1, 0, 3 lies on L1. To show that, we just substitute -1, 0, 3 for x, y, z and get -1 plus 1 over 2 is equal to 0 is equal to 3 minus 3, and we can see that it's true, hence the point -1, 0, 3 lies on L1. The next, find the vector equation of L1. To find the vector equation, we can equate it to some parameter, for example lambda, and just solve for x, for y, for z. So we consider this to be equal to lambda and solve for x, and we get that x is -1 plus 2 lambda. Consider this to be equal to lambda. We can see that it's just y is lambda, so we can write 0 plus lambda and consider this to be equal to lambda and get that z is equal to 3 minus lambda. Hence, our vector, its position vector of any point on the line is x, y, z, and it is equal just -1, 0, 3, -1, 0, 3, it's the position vector of some point on the line plus parameter and the direction vector of this line, and we can see that it's 2, 1, -1, 2, 1, -1. And you can see that if question is to get the Cartesian equation from the vector equation, you need just rewrite it x is, y is, z is, and just solve for lambda, and you can see that from this to get this you need just solve for lambda each equation. The next, consider the second line L2 defined by the vector equation. Find the possible values of A when the acute angle between L1 and L2 is 45 degrees. So it looks like this. There are two lines and each has a direction vector. Let it be B1, B2, and the acute angle is 45 between lines. So it may be like this, but also it may be like this, so that the angle between direction vectors is 135 degrees. And how to connect two vectors and angle? We can consider a dot product. And what is B1? What is B2? B1 it's the direction vector of one line, and B2 it's the direction vector of another line. So if we consider dot product of these vectors, 2, 1, -1, dot product A1, -1, we know that dot product B1, B2, it is equal to x1, x2 plus y1, y2 plus z1, z2, and also it is equal to the magnitude of the second multiplied by the magnitude, the magnitude of the first vector multiplied by the magnitude of the second vector and multiplied by the cosine of the angle between them. And for this problem, angle may be 45 degrees or 135 degrees, and we know that cosine of 45 is √2/2 and cosine of 135 degrees it's -√2/2. Hence, for our situation, our dot product is equal to magnitude of the first vector, it's the sum of squares of the coordinates, so it's 4 plus 1 plus 1 is √6, and the magnitude of the second it's a squared plus 2 and multiplied by the cosine, but to take into account both situations, 45 and 135, we can write just √2/2, but we can write plus minus in front, because there are two situations when it's cosine 45, and we get plus root 2 over 2, and the second it's when cosine is negative root 2 over 2. And what is dot product here? It's just x by x plus y by y plus z by z. So it becomes 2a plus 1 plus 1, or 2a plus 2, or we can factor out 2, is equal to plus minus root 6 root a squared plus 2 root 2 over 2. And we need just solve for a. How to do that? We can just square both sides and get 4a plus 1 squared is 6, a squared plus 2, and it's half, and we can divide by 2, and let open parentheses and get 4a squared plus 2a times 4, it's 8a, plus 1 times 4 plus 4 is 3a squared plus 6. Hence it becomes a squared plus 8a minus 2 is 0. So we get a quadratic equation and use a discriminant. So discriminant is b squared 64 minus 4ac times 1 times negative 2, and it becomes 72, and hence a is minus b plus minus root of 72 over 2, which is negative 8 plus minus, it's 36 times 2, so it's 6 root 2 over 2, and it's negative 4 plus minus 3 root 2. And it's the required values of a. And the next question, it is given that the lines L1 and L2 have a unique point of intersection A when A is not equal to K. Find the value of K and find the coordinates of the point A in terms of A. So it is given that these two lines have a unique point of intersection, and you can see that if we consider direction vectors, y and z coordinates are the same, and if a is equal to 2, we get that direction vectors are equal, and it implies that two lines are parallel and they may coincide or not, but hence they have no unique point of intersection. So to have a unique point of intersection, A cannot be equal to 2. So K is 2, and we need to find a point of intersection. How to find a point of intersection? We just equate x to x, y to y, z to z, and consider simultaneous equations. So we can write that 0 plus at 0 or just at is equal to negative 1 plus 2 lambda, 1 plus 1t is equal to lambda, and 2 minus t is equal to 3 minus lambda. So we get the next simultaneous equations. 2 minus t is 3 minus lambda, and we consider two of them, two equations, and solve for t and for lambda. So let's consider negative 1 plus 2 lambda is at, minus 2 lambda is negative 2 minus 2t, and we can see that we can add both sides and get negative 1 is negative 2 plus a minus 2t, hence t is 1 over a minus 2, and hence lambda is 1. We can use just this, lambda is 1 plus t, hence it's 1 plus 1 over a minus 2, and we can make a common denominator. It may be not required, but it becomes to this value. And notice that for this problem it is given that they have a unique point, so it's not necessary and it's not required to check the third equation. But in general, when you find the point of intersection, you should check the third equation. What does it mean? You should substitute the obtained values for t and for lambda into the third equation, and if you get that it's true, hence for these parameters you get a unique solution, a unique point of intersection. Otherwise, if the third equation is not true, it means that two lines are skew. It means that they do not intersect at a single point and are not parallel. So, to find coordinates of a point, we just substitute, it doesn't matter what parameter used. Let what is simpler, let use t, and coordinates, let's use these coordinates, and notice that it's in general x, y, z, it's coordinates. These are coordinates of a position vector. But what is vector? Coordinates of a vector are coordinates of endpoint minus coordinates of the starting point. But if we consider the position vector, the starting point is origin 0, 0, 0, and x, y, z are also coordinates of the point. So we get the same values x, y, z for position vector and for the same point on the line. So I can say that x, y, z are coordinates of a point corresponding to the position vector x, y, z. So hence x coordinate of a point is at, it's a over a minus 2. Y, it's 1 plus t, and z, it's 2 minus 1 over a minus 2. Hence coordinates are a minus 2, 1 plus 1 over a minus 2, and 2 minus 1 over a minus 2. And that's all for this question.